Clinical Genetics Fellowship in the Inter-Institute Medical Genetics Training Program at the National Institute of Health. She joined the faculty of Children's National Medical Center in Washington, D.C. in 1991 and became chair of the Division of Genetics and Metabolism in 1996. In 2009, she recruited to be at the National Human Genome Research Institute at the NIH to become the Deputy Clinical Director and to head the pediatric portion of the NIH Undiagnosed Disease Program. With the expansion of the Undiagnosed Disease Program to the Undiagnosed Disease Network, she's chairing right now the Clinical Protocols Working Group and has designed the phenotyping strategy for the undiagnosed network patients across the U.S. Dr. Tift's research interests for many years have been the lysosomal disorder affecting the central nervous system, particularly Tay-Sachs, GM1, gangliositis, and related disorders. So, without further ado, I invite Dr. Tift to give her talk.
First, let me thank the organizers of the meeting for allowing me to tell the story of the Undiagnosed Disease Program. This is a story that involves hundreds and hundreds of people, and I hope by using some examples of patients today, I can tell that story in a way that is faithful to the people involved and faithful to the patients. I'm supposed to tell you I have no conflicts of interest. I work for the US government, I can't have. And what I wanted to do at the beginning was really to acknowledge many, many people who've been involved in this project. Hillary Clinton says it takes a village, and this is part of our village. The boss of our village here is our director, Bill Gall, and many, many other people who've been involved, including many collaborators. This slide could go on for 4 or 5 more collaborators internationally, nationally, and throughout the NIH. Okay. So why are undiagnosed diseases important? I think all of you who work in the rare disease community will realize that every rare disease was once an undiagnosed disease. So the diseases that we're diagnosing are not only rare, in most cases they're ultra rare, and in some cases they are unique. About 6% of the patients who contact the Office of Rare Disorders, who Steve Groft used to head, were found not to have a diagnosis at all. And I think this painting that hangs in the British Museum really says it all. I mean, this is a child who's ill in a very poor household where they don't even have a bed. They have to put the 2 chairs together. This is the distraught parents who really feel like they have nothing else they can do and don't know where to turn. And actually the physician, who is supposed to be the learned person who is sitting there looking at the child and observing her, maybe doing some phenotyping, but has not yet come up with a disease. So the unmet need was, of the 6,000 calls that came to the NIH Office of Rare Disorders in 2007, nearly 400 of them were patients who did not have a diagnosis. And as Yaffa has also told us, of the callers who did have a diagnosis, 33% of them took up to 5 years to get that diagnosis, and 15% of them took even longer than 5 years. And I think this is something that everyone in the audience could pretty much resonate with. Okay, so then there was a dream, and the dream was the NIH Undiagnosed Diseases Program. It was launched in May of 2008 as a 5-year pilot project, and the 2 objectives really were the objectives of the NIH. That is public service, to provide answers to patients who had very mysterious conditions, who'd been all over the country and in cases all over the world looking for a diagnosis, and to advance biomedical research. Our theory was that if we could find very rare diseases, they would generalize to more common diseases, and we might be able to find treatments not only for rare diseases, but also for more common diseases. And these are the dreamers. This person you will recognize immediately, Steve Groft, and this person, my boss, Bill Gall. And as we just heard from our Indian friend, if it's a dream, it's only one person. If it's more than one person, it's not a dream, it becomes a reality. So I want to tell you how that actually came about. You'll see this slide, or one similar to it, and all the way through the presentation, and it basically describes how we take our families through the process. So we begin here by comprehensive record evaluation and by selecting families. So I want to talk to you about that first. The way it works is patients hear about the program over the internet from other physicians, from other patients, and as we know, patients are very resourceful, and in most cases with the undiagnosed disease program, it was the patients who found us. They send their application, we acknowledge that, and we ask them for their entire medical record, which also can include x-rays, photographs, pathology slides, and all of this comes to our offices. We organize the charts, we scan them electronically. Dr. Gall and I triage the records to appropriate specialists at the NIH and sometimes even outside of the NIH to review the records, give us their recommendation on whether or not they think it would be a good case for us to admit, and then patients and referring physicians are informed of the decision. Now this is what it actually looks like in the office. This is kind of what it feels like. And at one point in the process, we actually had to suspend taking applications for 6 months because we just couldn't process them fast enough. Okay, I like to say all of our applicants are desperate, and everyone gets something from the undiagnosed disease program. They get a record, which they have sent to us, that gets organized and scanned, and in some cases, families have never even had entire copies of their medical record. Applicants that are not accepted, and that's about 75% of them, receive a personalized letter that says, we've reviewed your case, and here are some specific recommendations we would give to you for further evaluation, even if we're not going to take you. About 25% of the patients are accepted. They come to the NIH Clinical Center, which is right here, to receive a 1-week inpatient evaluation. I'll show you what that looks like at the NIH Clinical Center in Bethesda. So who is most likely to be selected here? Now, most of us are geneticists, pediatricians, internal medicine folks, and we're trying to choose the things that we think that we can have the best chance of solving. So those cases might be cases that have objective physical and biochemical findings, something that was completely evaluated in the academic setting already. These are people who have often, in most cases, been to multiple tertiary care centers, Johns Hopkins, the Mayo Clinic, the Cleveland Clinic, before they even apply. The family structure for genetic diseases matters to us when we do whole exome and whole genome sequencing. It's nice if we can have both parents available to give blood samples for DNA. If there are additional family members like siblings that have the same condition and it's more likely to be genetic, they're more likely to be chosen. If there's an unaffected sibling that we can use to filter variants, I'll talk about this a little bit later, that's helpful. And families in whom both parents are related to each other by blood sometimes also helps. So as of last Monday, 2008 through 2015, we had about 7,500 inquiries. We had reviewed medical records on over 3,000 patients. We had accepted almost 1,000 of them. Of those, 36%, or about 350, were children, the rest were adults. About half and half, male and female. And about half our patients had a neurologic phenotype, which only tells you that the brain is the last piece of uncharted territory to really come to understand. In the pediatric program, we've made a diagnosis in 93 cases and about 33% of the time. It's a little less than that if you combine them and you add the adults in, and that's really because in the adult scenario, often parents of the adults are not available to give blood to help us. Okay, so the major phenotypes that we see of the applicants, you'll see a lot of these, 51% of them have a neurologic basis. We are more likely to accept those. We're probably less likely to accept patients who have sort of a generalized fibromyalgia. So this gives you an idea of the types of things of people who are applying and the types of people we're likely to accept. In the pediatric population, you can see there's sort of two humps. This hump, kids about 3 or 4 or 5, are really children who have had their disease since they were born. They were born with it. And they've been searching for a diagnosis for 3, 4, 5 years. This other bump are patients who were born healthy and started showing symptoms of their disease when they were 3, 4, and 5 years old, and now 5 to 6 to 8 years after the fact are applying because they've been all over the country and they can't find any answers. Okay, so we bring them to the clinical center for extensive clinical evaluation and testing and to collect biospecimens for DNA, urine, and other things. Phenotyping. I stress to my team that phenotyping, which is defined as, right here, the observable properties of an organism that are produced by the interaction of the genotype and the environment, is the most important thing. If we don't get the phenotyping right, trying to interpret the exome or genome sequencing is impossible. So careful phenotyping is everything. So when we talk about phenotyping, we talk about starting when the charts are reviewed, writing down symptoms that cause us to take the patient in the first place. They get more focused as we receive more information. During their 1-week evaluation, obviously we're collecting most of the information. And then when part of our diagnostic testing comes back, before we flip into the research mode, we're getting more phenotype information. This is a typical schedule of a child who comes to the NIH for evaluation. This is Monday through Friday, and you don't have to be able to read this, but the point is they really get through the paces. I tell my patients when they come on Monday morning, there's good news and there's bad news, and they're both the same. The good news is you're going to get a year's worth of evaluation in 1 week. The bad news is you're going to get a year's worth of evaluation in 1 week, and you are going to be exhausted. And usually they are. So it begins with informed consent. This is a research project. We're not just seeing patients in a clinical setting. The patients actually have to give informed consent to be involved, and every single thing they undergo is entirely voluntary. There's a sedate day, which I'll talk about in a minute, that's turned out in the pediatric population to be really, really critical. And then there's a wrap-up session at which we let the patients ask as many questions as they want, and we give them an entire copy of the medical record when they leave the NIH. And we remain available to them to kind of feed back more information as it becomes available. Now, sedate day for us is really a choreography. It is really a dance of trying to work together with a pediatric anesthesiologist to allow the children, because most families really don't want their child, as you can imagine, to be subjected to hurting procedures while they're awake, being continually stuck or catheterized or what have you. The MRI scans of the brain that we do on most of our children last 1.5 to 2 hours. No child really can lay still that long. So the kids are, with our pediatric anesthesia folks, we put them to sleep for 3 to 5 hours. They go into the scanner, they come out of the scanner, they're wheeled across to a small room where we can do a number of procedures if we need to. A spinal tap, a skin biopsy, eye exam under anesthesia. Now remember, most of these are children who can't cooperate. Brainstem evokes potentials for hearing, a dysmorphology exam if we need to get very good measurements on the children while they're asleep is a great time. Sometimes, because the children are neurologically compromised, getting dental care is very difficult, so we can have our dentist come and look at them. Nerve conductions, EMGs, if we need to get extra blood, we can do it then. If we need a urine sample, we can catheterize the child for urine. And in some cases, the parents have said, for example, we had one child whose ear tube had ear tubes placed and one had fallen out. We actually had our ENT doctors come down and pull the ear tube out, the non-functioning ear tube, while the child was asleep. So we try to do as much as we can in that one sedation day. And I can tell you that there's really no place else in the country that I know of that people have been able to coordinate this type of sedated care. We've done now over 100 cases in our kids, and so far we haven't had any difficulties. Knock on wood. Okay, so in the first 5 years of the pediatric part of the program, we saw 193 families, 215 patients, because some of these were siblings that had been affected with the same condition. We diagnosed about 26% of them. That's a little higher now, as I showed you. But interestingly enough, about half the diagnoses came from doing next-generation sequencing, exome sequencing, but about half of the time, we were able to just use conventional testing based on good phenotyping and come up with an answer. Now that many of our patients have had clinical exome sequencing before they get to us, that's going to be a little bit less, I think. Okay, so now we begin family exome sequencing and single nucleotide polymorphism. Some people call this a microarray chip, and looking for strong candidate genes that we think will explain things. I'm going to go through each of some scenarios that I tell our patients we're looking for and how their diagnosis could play out, and I'm going to use our patients to tell that story. When I talk to the moms and dads, I usually say, this is usually either an extremely rare disease, it's more than one disease, it's a very unusual presentation of a more common disease, and even by more common I mean still a rare disease by our standards, or it's an entirely new disease. And I'm going to give you some examples of all of those. Okay, this was a 5-year-old child who came to us with abducted thumbs, and I realize that not all of you in the room are medical, so I'm going to, or scientists, and I'm going to try to make this as clear as possible, so like don't glaze your eyes over, because you will get through this. Okay, the child had club feet, low muscle tone, and a bleeding disorder. You can see here when this child is using a bar for his club feet. But even with, this looks like a child almost with hemophilia. Even with minor trauma, he got these huge bruises. When we saw him at age 5, you can still appreciate that he had lots of bruising. In his knees here, in his shins. His very flat feet, very stretchy, hyperextensible fingers and toes. And his parents happened to be related to each other. This was a child from, his parents were from Mexico. He was actually a child from Texas. And his parents were distantly related to each other. So it turned out that the child actually had a small region on one of the chromosomes that he had inherited from both his parents. And in that very small region, there were 72 genes. One gene of those 72 seemed to fit the clinical picture called CHST14, in which this child had a single base pair change, a G to a C, right here. CHES14 codes for dermatan 4 sulfotransferase 1. Okay, so that basically it's involved in the formation of dermatan sulfate, which is fibrinolytic, meaning it breaks down clots. And it's actually been, it never made it quite to clinical trials, but it was actually thought about along with heparin as being something that you might use to anticoagulate folks who needed it. But we had the idea that perhaps we could prevent the bruising by treating this child with dermatan sulfate. The problem was there was no available good manufacturing practice source of dermatan sulfate that we've been able to find. Now, this child was the first child in North America that we knew about. We found another child in Europe, and a few children have subsequently been found. And this child we saw in 2009. This paper was just published in 2015 that actually talks about a handful of other children that we actually lumped together with this diagnosis. And just at the American Society of Human Genetics meetings last week, a Japanese group presented another large cohort of Japanese patients that have the same mutation. So perhaps this is not quite as rare a diagnosis as we think it is, but people just haven't recognized it until now. Okay, extremely rare disease with an expanded phenotype. These are two brothers, this is my nurse practitioner Gretchen, that we saw together, and they simply had low muscle tone, severe intellectual disability, neither one of them could walk, and they were completely dependent on mom and dad for their care. You can see here, these are the brothers. As it turns out, by doing whole exome sequencing, and I'll show you the details in the next slide, and using DNA from these two affected brothers and one of the unaffected siblings, we could ask the question, show me all the situations in which each parent passed a mutation in the same gene, and it turns out in this case to be MED23, to this child and to this child, but not to these children. And to make a long story short, MED23 is one small protein in a huge complex that's a transcription factor. And what expanded the phenotype here, there was only one other case report of mutations in MED23 in, I believe in Turkey, where the patients were two adults with mild mental retardation, but who could also care for themselves. So these children were a lot worse. It also turns out one of the other subunits here is a gene that affects heart formation, and both of these boys actually also had congenital heart disease, a common problem in children, but I think the two of those things together probably explain why this was the mutation. And the way we found this was Basically, this is an exome sequence, and each one of these little lines here that go across are little bits of sequence, and you line them all up. And this is from